So I have uploaded the last 2 weeks a video to YouTube. Okay, and I don't know whether that is the reason for people late joining or not joining in the live session. So we'll wait for maybe 5 minutes more and then we will actually start. So nobody wants to. Okay, Isha has put a message. Going through the concept and after that solving questions related to same topic from book and previous gate questions. Okay, that is good. So how are you going through the concept? Like you are going through the concept you through books and your college notes? Okay, okay. So if anyone is starting now and they don't have any basics, then I think they should target 2024 rather than 23. You should give 23 as well, but your main target should be 24, and then you should prepare likewise. So last class I think I had shared the preparation strategy you should follow and the way you should prepare. Okay. Mm, okay, 2-3 minutes more and then we will start. So today I will start with JFET. Okay, I earlier this JFET questions, DC biasing questions were very much prominent, but now I am not seeing them much. But that means that if a topic has not been touched for 3-4 years, I'm sorry, it's actually raining heavily here. So I'll repeat whatever is missed. So the thing is that for GATE 2022 or 2023, if there have been questions that are not being asked for last 4 or 5 years, there might be a chance that it is asked for a 1 mark question or something, and there is a high chance that the topic of JFET and MOSFET, those multiple select questions that are there, in that theoretical it can ask, okay, or like theoretical aspects it can ask. For example, it can say like the multiple select question is like that, right? That select whatever is correct, right? That. So they might say that the statement might say JFET is having low input impedance. So you should know that JFET is actually having high input impedance. So that will make the statement wrong. So like that, theoretically, multiple select questions can be asked. So I have some questions here. I will take them. For Chandrasekhar is asking, ma'am, for analog, I saw the IIT Madras sir's video. There are 39 videos and I don't know what are the video I should watch or leave. Should I watch the whole series? Chandrasekhar, if you are having time, say you are targeting 2024, then you should watch everything. Okay. If you are targeting 23, then you should select. So now how will you select? You go to NPTEL site, in there transcripts is there, like I was showing you in the EDC. So transcripts are usually there. In the transcript you can quickly browse through it and see what all topics he has touched, and just watch that topic and leave the other. Okay, but it will be good if you but that actually breaks the continuation. So it will be good if you can watch everything, but if you are short of time, then I would rather suggest you to search topic wise as well. Like there can be other videos in YouTube which you can watch, not necessarily the NPTEL video only. There can be other videos also by other professors which are or other teachers which are very much particular to the topic, that also you can watch. Okay, these are, I know these are long videos. So 39 videos, 39 videos means 1 hour per video is 39 hour. That 1 hour is only for video watching. For understanding, writing, you take half an hour more. So I take 1.5 hour per video. Okay, so 1.5 hour per video, plus if you want to revise the previous concept, then half an hour more. So if I take 2 hour per video, then 39 videos makes how much? 39 into 2, 78, right? So that means 78 hours you have to put in one subject. Okay, so 80 hours, let's say that 80 hours per subject, you have 8 subjects, 8 technical subjects if I'm not wrong. Please correct me, how many technical subjects are there? Networks, signal, communication, analog, digital, control. This makes 6. What am I missing? EMT, 7, and maths, I think. EDC and analog are together, I guess, or EDC if you'd want to take separately. So 8 subjects like that. So 8 into 80 will make 640 hours, right? So if I assume that all of you are pass outs and you have only this like studying job to do, and you have 1 hour, 1 year in front of you, that you are, if you are targeting GATE 2024 and you want to watch all the series, then 640 hours is what you will have to give in the entire year. Plus you have to take time for preparation also. So let me write. Let's discuss this a bit and then we will start with JFET. So I see there is actually 50% attendance today till now, and last time it was 36 students. Today there are 19. It might be because I have shared in YouTube. So it's better if you join the online class as well. Otherwise, it does not make any sense to have it, because recorded videos you can get anywhere, but live interaction is something you will not get. Okay, so if I have 8 subjects to do and I 80 hours per subject is the NPTEL video, then I give 640 hours total I need. So starting from now, if I say, or let's say you start after GATE 2023, so if I start from January 2023 to next Jan 2024, then I think, according to me, from October to Jan you should completely practice. Okay, by before October you should already know the concept. That is what my idea is. So basically from Jan, okay, so basically from Jan to October you should be able to finish off this 640 hours of lecture plus revision plus book questions plus previous year. So this should be your target. So by next year October you should finish everything, and then from October again you only start practicing and give tests, like uh, the practice tests, that test series are there, so you should give test series. Okay, so this is my idea of preparation. This is how you should do. Any questions on this? You can unmute yourself and tell me directly instead of typing everything. Any questions? Okay, so let me start with JFET. So as I see there is 50% attendance today. So what I will do is I will upload the videos a bit late. I will not upload them very soon enough. Okay, so that the attendance is maintained in the class as well. And if you know your friends who are coming or joining and now they are not joining, please tell it to them that if the live sessions don't happen, then there won't be any videos to upload to. Okay. Okay, so I'll just start with the JFET today. So JFET is junction field effect transistor. So there are basically two topics in GATE which will be asked. One is JFET, another is MOSFET. Now MOSFET is more important and it has been seen that mostly questions come from MOSFET. But to have an idea, we will go with JFET as well. Okay, so JFET and MOSFET differ in the uh, construction. Okay, so there is a difference in the construction and therefore there is a slight difference in their working. Now in JFET, both are high input impedance devices, but in MOSFET, the input impedance is higher. Okay, there is a reason for it. We'll see what the reason is, but the input impedance is higher. So what basically happens is that there is a substrate. So here it is an N substrate. Okay, so if it is an N substrate, then it is an N JFET. Okay, and the channel and there is this P plus region. You can see there is this P plus region around the gates. Okay, and therefore there is this pink color is the depletion region. Okay, so basically this area is the depletion region. Since there is a PN region, there is a depletion region which is created. Okay, so what we do is that, see, this is the depletion region and the area which is not there in the depletion, that acts as a channel. Okay, so that area acts as a channel. So what happens is, with the help of the drain to source voltage, that is, this terminal is a drain terminal, say, and this terminal is a source terminal. So with the help of the drain to source voltage and also gate to source voltage, so there will be two voltages. One will be between gate to source, okay, and the other will be between drain to source. So with the help of these two voltages, basically we try to make sure that this device works as a transistor. Okay, this device works as a transistor. So basically what we try is that we try to control the voltage of one particular terminal, and that leads to change in voltage or current in some other part in that particular device, leading to transistorized action. These photos I have taken from Donald Niemann's book. You guys can refer that book, is very good for solving examples. I think I have mentioned it in the other class as well. Donald Niemann. Okay. So it is having very good examples and we will solve 3 examples from this book. And likewise, those kind of examples have been asked in GATE as well. Okay. So yeah, so let's start. Basically, a JFET and MOSFET works as an amplifier in saturation region. Okay, so what happens is that so this is a curve you can see for with current ID, drain current, with respect to drain to source voltage VDS. So what happens for very low value? So this is basically a very low value of VDS, very low value. This is a very low VDS region. Okay, so for very low VDS region, the behavior is almost linear, right? That means the JFET works more or less like a resistor. A linear curve, a straight line between current and voltage, is nothing but a ohmic characteristic, right? Ohmic characteristic. Okay, So this basically starts behaving like a resistor, and this slope will give you 1 by R, right? So basically it is having unit of GM, transconductance. Okay, so now in this curve you see in the second diagram, first is when VGS is 0. If when VGS is 0, we saw that there is one straight line which is coming, right? Now next is we have applied some VGS and you see it is a negative voltage, right? So what happens is when you start putting a voltage here, the depletion region starts increasing, and there will be a point where the depletion region actually touches it each other, and this region is called pinch off. Okay, this region is called pinch off, turning the device off. Okay, turning the device off. So this is one main difference between the JFET and MOSFET, that JFET is a on device. That means as soon as you connect a voltage between drain to source, as soon as you give VDS, the JFET will start working with VGS 0. Okay, but as you start making VGS more negative for N channel JFET, for N JFET, if you start giving VGS more negative, it will eventually turn off at some particular value of VGS. It eventually turns off. Okay, and what happens in MOSFET? MOSFET is actually, so JFET we saw it is a normal on device, and MOSFET is basically of two types. One is depletion mode, another is enhancement mode. In enhancement mode, the MOSFET is initially off. Here it is initially off and then turns on. But in depletion, the MOSFET just behaves like a on device. It is initially like it will turn off after some time. Okay, so we will go through this in the next class. Okay, what is depletion and enhancement and all. Okay, so let's come back to JFET. So I hope this is clear that, so what is happening is, if you see the characteristic, if this is VDS and this is ID, this say is your relationship at VGS 0 volts. So how this relationship is coming? You are basically, suppose you have a JFET. So the symbol of N JFET is like this. Okay. So suppose this is drain terminal, this is drain, this is source. What you did, you took a JFET and you basically connected a source here, some positive, and you can vary this. Let's say it is a DC generator, you can vary this. Okay, and here you have fixed this to 0 volt. This is fixed at 0 volt, VGS. So VGS is fixed at 0 volt and you are varying this VDS. You are varying the VDS and you have an ammeter connected here. Okay, you have an ammeter connected here which is basically reading. So this is not a current source, I should not draw it like this. So this is basically a ammeter connected here. Okay, and you are monitoring the current which is ID. Is this diagram clear? Any questions? So I have given you a JFET and you have made this connection in breadboard. Now what you are doing, you are increasing the VDS value slowly. Okay, from 0 to 0.1 to 0.2. I am just taking arbitrary value. Okay, say to 1 volt you will go. So you are seeing this kind and you are monitoring the current and you plot the graph and you see this kind of a behavior. Mark that I have not made this as a straight line but something tapered. We'll see why tapered. So this is basically at VGS 0 volt. Now what you did, you connected a varying source at VGS also. Now you started varying VGS. So always remember, in NFET VGS is negative. VGS goes to negative values. Okay, that turns off the device. So basically it starts behaving in this manner, and slowly there will be a value where it will be completely zero. So this will be the point where VGS has actually become equal to VP. And in other places VGS is starting like this, might be VGS minus 1 volt, VGS minus 2 volt, VGS minus 3 volt, VGS minus 4 volt, and let's say this was VGS equals to VP something like minus 5 volt or something. Okay, so I am taking very much arbitrary values. Okay, so this is how it works. So this and this slope, basically this slope results because of the presence of another parameter which is called lambda, which actually makes the current of function of VDS as well. So here you can see that with varying VDS your current will behave like this. So in this slope, if it is a straight line, that means what? The current has become constant after a particular VDS. But if it starts behaving like this, then means there is a presence of a third component. There is a dependence on VDS also, apart from VGS. That happens because, so this is given by the equation ID is equals to IDSS 1 minus VGS by VP. Okay, 1 minus VGS by VP square. So 1 second, 1 minus VGS VP square, and the slope actually results in another term which comes in a multiplication. Okay, we'll see this topic in detail in next class when we go with MOSFETs. So right now you can just see this expression, and always remember that normally in gate this is what is asked. So for gate the equation that will come in handy is this. Okay, this is the equation that will come handy. Okay, so I have told you the symbol also. So for NFET the symbol is this. For PFET the symbol is like this. Okay, for NFET VGS is negative, BP is also a negative value. Okay, and here VGS is positive, VP is also positive value. Okay, and here VGS will be always it will be always less than VP, so mod VGS will be always less than mod VP. Okay, same here. Now I'll tell you the trick to how to solve the question. So let's start the question and then we can go to the trick. Okay, so I'm going to solve the question from Donald Niemann's book only. So till here, is there any doubt? Anyone wants to ask anything? So basically in PFET, the voltages will start becoming positive. In NFET, it will start becoming negative. Okay. Is it fine? Okay. So let's then start with first problem. The first problem says that calculate ID and VDS SAT in an N channel PN JFET. Okay, so it's an N channel PN JFET. So that means as I had shown in the diagram, this will be P plus, this is P plus, and this is N. Okay, this is the N region. So for the N channel JFET. Okay, so now IDSS is the saturation current. Okay, IDSS is the saturation current. When VGS is 0 volts. Okay, so that means it is the maximum current. And with the change in the dimension of the device, with the change in dimension, that is the width of the JFET, we can increase IDSS. So this is an important point to remember. It can be asked as an MSQ. So we can increase IDSS, okay, and therefore increase the current handling capacity. So when we study MOSFET, I will tell you what is the con of this part, what is the downfall of this increasing the dimension of the JFET. Okay, what happens, what is the negative thing that happens. So this will actually increase the current, okay, if you current capacity of JFET. Okay, so now next is, let's see, so this point you guys please write, and after that I will go ahead. I'm giving you 1 minute. Just note down this question as well as this point. I'm giving you 1 minute. Okay. Please let me know once you have noted the question and the point down. So Ramesh has noted. Anyone else? Please respond if you have all have noted it down. Okay. So now let's start with the solution. Okay. So what is being told? So they have given IDSS value 2 milliampere. They have given a pinch off voltage minus 3.5 volts. Please note this, it is an NFET, so therefore the VP is negative. Now they have asked find ID. So I am going with the first part first. Find ID for VGS 0 volt. Then VGS value is VP by 4. Then the VGS value is VP by 2. Okay. So now you know that the formula is ID equals to IDSS 1 minus VGS by VP square. Now always remember, when you are putting the value, suppose VGS, here you have been given VGS, right? So whenever VGS and VP both are given, you have to take it with the sign. Okay. For example, first let me solve it for VGS 0 and then I will go to that, what I am trying to explain. Otherwise that will give you an error while solving. So ID is equals to IDSS 2 milliampere, right? I am writing the unit deliberately right now. 1 minus VGS is 0, VP is minus 3.5. Okay, so this gives nothing but ID equals to IDSS equals to 2 milliampere, which we have seen. I had told you that it is the maximum current which will flow when VGS is equals to 0 volt. Now see, in the second case, they have given VGS is equals to VP by 4. Now, if I try to write ID equals to IDSS, 1 minus, this is VP in denominator. Here I will write VP by 4. Note that both of their signs are equal, right? So if I write VP as minus 3.5, VGS will be minus 3.5 divided by 4, so that this minus sign will cancel out. Okay, and this term will always be in, the entire term will always be in negative to 1. Okay, but this is not the case when we have to find out VGS, and that I will show you. Okay, so let's go from here. I hope this is understandable. If not, you can unmute yourself and ask me again. So I have just put VGS equals to VP by 4, and now you cancel VP, and IDSS is nothing but 1 minus 1 by 4's whole square, right? So this is nothing but IDSS into 3 by 4 whole square, IDSS into 9 by 16. This gives you 2 into 9 by 16, which gives you 9 by 8 milliamperes. This is the value of ID. Okay. So can you calculate and tell me what is 9 by 8 coming as? Make a quick calculation. 1.125.
1.125.
Okay. So now in the third case, can you guys please solve and tell me the answer? VGS is given as VP by 2. The formula is this. Can you quickly do it and tell me the answer?
2.25
Are you getting 2.25
milliamp.
milliamps?
Yes.
No, you have done something wrong. So who said 2.25? I did not see it. Yeah, so who had got 2.25? I just
6.5.
want to know, like, no need to be any afraid or anything. So Shashwat, as I had mentioned that
Me, ma'am.
2 milliampere is the current which is the highest current, right? So as soon as you got 2.25, you should know that you have done something wrong. You understood? So if this question have come in numerical answer
Yes,
type,
yes.
then there won't be any option, right? And suppose you got 2.25, so you are going to write that. So this is one of the things from where you can actually cross check whether what is correct or not. Am I clear? This is for everybody because this mistake can be from everybody, any one of you.
Okay. Yes, ma'am.
Okay. So now did you get the correct answer, Shashwat? Please solve. Please solve it again. So how are you solving?
No, ma'am, right now.
ID, right, 2, and 1 minus VP is 1 VP
Just
by
putting the
2,
values.
and this is VP. So VP cancels out. There is a square here. So this will be 2 into 1 minus half square, right? So this will come 0.5.
Yes.
Okay.
Okay.
Okay. Now say
Yes, ma'am.
I have given you that ID is, I have given that ID is zero point 0.5 milliampere, VP is minus 3.5 volt. So is everyone done? Should I proceed or not? If anyone is not done, they can just tell me because I want everyone to be on same page. Okay, so since nobody is responding, I'm guessing that you all have done. So say I'm saying that ID is 0.5 milliamp, IDSS is 2 milliamperes, VP is minus 3.5, and I'm asking you to find VGS. Okay, so now how will you solve the question? So you know that the formula is ID is equals to IDSS 1 minus VGS by VP whole square, right? So you will put in the values. 0.5 equals to 2, 1 minus, now you remember I had said that put the VGS with the sign, right? So but here I have to find out VGS, then I have to put VP with the sign. This will be minus 3.5. Don't put mod value here. If you are putting both VGS and VP value, then you will have to put both with the sign. Okay, so whatever you put, you have to put with the sign. But if you're finding VGS, don't put it with the sign here. Okay, so for example, if I am asking you to find IDS, then what will you do? You will put, say VGS is, let's say, minus 1 volt. So what you will do? 2 into 1 minus minus 1 minus 3.5 and then whole square. Okay, but when you have to find VGS, you have to do it in this way, so that ultimately your answer will come in negative. Okay, so we'll see this. What will happen? If you now solve this, can you quickly solve this? This is what was given to us, right? You remember? I have just taken the example of VP by 2. So the third part where VGS was VP by 2, we were getting ID as 0.5. So I just took this example and I asked you to find the VGS. So that means VGS should have come to be VP by 2. So you see here, now when I have solved this, VGS is coming to be minus 3.5 into 0.5. That is nothing but minus 3.5 into 1 by 2. Minus 3.5 is nothing but VP by 2. By 2 is from this 1 by 2. Okay. Is this clear? So whenever you have been asked to find VGS or VP, you can be asked to find VP as well. Okay. In that case, you only take one of the sign. Don't make VGS negative there. That is only a variable. Ultimately, when you have solved, VGS will come to be negative. Like in this case, VGS came in to be negative, right? And then I have written it in terms of VP by 2 so that we can verify, because I have taken it from the question. Is this clear? If it is not clear, please prompt me. I'll again explain it to you. Okay, very well. So now I'm going to the next question. Okay, and then the third question, all of you will solve it. I will not solve. Next question I'm going to solve. Okay, so please take a note of this question. This was in Donald Niemann's book, and I will suggest all of you to solve that book. That is a good book with good examples. Okay, so second question, problem 2. In the problem 2, you basically have to design a JFET. Okay, so what is meant by designing a circuit? That means you have to find out certain variables, certain components values. Okay, so what will happen here? See, you have been given IDSS. So note the question first quickly. Note the question first. Till then I am just writing the formula. You guys note the question. So basically here if you see, you have to find the value of RD because RD is not given. So to find RD, right, and R1, R2. This is what we have to find. Okay, should I start the solution? Okay, have you noted? Should I start the solution? Okay, so now these are my given stuff. Okay, so this is what is given. So now what we can do is we can find the VG value, right? I can find VG. So what will be VG? How to find? So let's apply. So there is two methods to find. Those who are pro in KVL, KCL and voltage division, they can directly write it, or otherwise I will just show you like a beginner. Okay, so whenever 5 volt is given to you, the way I apply KVL I will show you. So whenever 5 volt is given, this means this terminal is connected in this way. This is what plus 5 volt means, and minus 5 volt means this is connected in this way with respect to ground, you see. Okay, with respect to ground. So here ground terminal is connected to positive, here ground terminal is connected to negative. Okay, so now when you apply KVL, how I apply is, if I choose this path, see the green line, if I choose this path from this ground to this ground, right? So how I'll do is, when I enter a voltage source, if I encounter a negative sign, I just use negative. So I'll just write -5. Is this clear? So I'm encountering minus, so I'll write -5. Then from here I'll decide a current direction. I'll say I am going this direction, I. I'm saying I is this direction, okay? And I'll take the voltage across the resistance to be positive. So what I'll write, -5 plus IR1. Since this is a high input impedance, this is zero current here in here, and the I, same I will flow from R2 as well. Okay, this is zero current here, 0 amperes. So same current I will flow from here. Okay, so therefore I will write plus IR2, and then since I am entering minus here, I will write -5 equals to 0. Is this clear? Or any doubts in this? I'll repeat. Whatever I enter, whatever source I enter, voltage source, if I encounter a negative sign, I'll write -5. Then according to the direction of current, if my direction is the same direction as that of the given direction of current, everything will be positive. The voltage drop across resistor will be positive, and I'll write plus IR1 plus IR2 -5 equals to 0. This gives I is equals to 10 upon R1 plus R2. Okay, now I asked you to find VG, right? VG is this voltage. So whenever you are coming from a node, so when you are starting from a node, what I'll write it as minus VG plus IR2, because I'm going in this direction. I'm going in this direction only. I will take this path. Okay, so minus VG plus IR2, -5 is 0. So VG will be IR2 -5. Okay, so putting the value of I from above, VG equals to 10 times R2 by R1 plus R2 -5. You could have also followed this path and found it. If you will follow this path, how will it come? -5 plus IR1 plus VG equals to 0. You are entering into the node, that will make it positive. Okay, when you are going from the node, that is negative. In this path I was going from the node. In this path I am entering to the node. Okay, basically this node is nothing but like this, plus minus Vg. Let me draw it clearly because this is an important application of KVL KCL. So suppose this is plus 5, this is minus 5, and here I have Vg. This is R1, this is R2. So this circuit is nothing but like this. So in this way there will not be any confusion. Otherwise people are very much confused as to what to take as minus, what to take as plus, what drop to take what. So there should not be any confusion here. Okay. So 5 volts. 5 volts. Okay, whenever you have made the voltage source in this way, minus plus, don't write minus 5 because you have already said, like showed that with respect to ground it is negative. Okay. So this is R1, this is R2. Now suppose I am already taking that the current direction is I here. It is given in the question or whatever. Okay. And Vg, if I say what is Vg's direction, then Vg is like this. Positive voltage means it is with respect to ground positive. Okay. So if now I have to say apply KVL. So if this is my direction of KVL like this. So what I'll do, if I'm entering the voltage source, I'll write minus because I'm encountering minus sign first. So minus 5. Voltage at resistor will always be positive if your direction is as the same direction as current. If in my question, the given direction, say if my question was like this, that find I and the direction is top side and you are applying KVL in downside, then I will ultimately be negative of what you are getting. Is this clear? Chandrasekhar, is this clear to you? Mamta, this is clear? Okay.
Yes, ma'am.
So this is minus 5
Yes, ma'am.
plus, or in this case, since I is in this direction, minus IR1 plus Vg equals to 0. Okay. So this is how you should apply. So you can take a photo or write it down as you wish. Okay. If your KVL direction is this, then you will not take the drop across R as positive. So in this case, what will be your I value? Let me draw it in red only. So in this case, I will be Vg plus or minus Vg plus 5 by minus R1, right? So basically 5 minus Vg by R1. Now if the green is your direction, then it is minus Vg plus IR1 plus 5 equals to 0. Then I is equals to what? Vg minus 5 by R1. I have done some mistake. Where have I done the mistake? So minus Vg plus IR1 plus 5 is 0. So in this case it is minus 5 minus R1. Yeah, it is correct. So okay. This is, I have written it wrong. Vg minus 5 by R1. Okay. So basically whichever direction you apply the KVL, you will arrive at the same solution if everything is correct. If your concept, like the way you are doing is correct, then you will arrive at the same solution. So with this concept in mind, I hope this is clear why I have written Vg is equals to 10 times R2 by R1 plus R2 minus 5. Okay, this can also be understood with voltage division concept. So with voltage division, what is Vg? It is the total voltage into R2 by R1 plus R2, total voltage plus 5 minus 5 is 10 volt into R1 R2 by R1 plus R2 minus 5. Okay, because one node is already connected to 5 volts, so that you have to subtract. Okay, so from here we have already arrived at Vg. Now if I can find Vg, so let me just erase everything. So in this question VDS is given, that means plus minus 5 volt is given here. Okay, this current, you know, you know ID 5 milliampere. Okay, so that means you can find VGS. First point is you can find VGS. You can also find, since this is 5 milliampere, okay, you can also find Vs, right? So let me redraw this. Vs will equal to, so minus Vs plus IDRS minus 5 is 0. So Vs is equals to, I have applied KVL here. Okay, Vs is equals to 5 minus IDRS. Okay, so RS is given 0.5 K. ID is given, what was ID? 5 milliampere. Can you tell me what is Vs? Please tell me what is Vs. So one more trick here. If your ID is given in milliampere and your RS is in kilo ohms, do not change the unit. If you will multiply, you will automatically get voltage in volts. See, what this will come? This will come to be 5 volts minus 5 milliampere is 5 into 10 to the power minus 3 amperes into 0.5 into 10 to the power 3 kilo ohms, right? So see, this will always cancel out. So whenever your value is in milliampere and kilo ohm, the output will be always in volts, right? So you need not convert it. That will eat up your time. So you need not convert it. So directly you can say 5 minus 0.5 into 5. So 5 minus 2.5 is 2.5 volts. Is this clear? Is this clear? Shashwat, is this clear? Okay. Then Vs I have got.
Yes,
I
madam.
have got Vs to be 2.5. Now VGS also I can find because IDSS is given. Okay. What is IDSS? 12 milliampere. Maximum current of JFET 12 milliampere. VP is minus 3.5 volt. VGS I have to find out. ID is 0.5. Can you quickly do the calculation and tell me what you are getting? So 0.5 equals to 12 into 1 minus VGS by minus 3.5 whole square. Right? So 0.5 divided by 12 is 1 by 24. If I take a root of that, that will be root 6 by 12, that minus 1 into 3.5. I am getting this value. You guys tell me if it is what you are getting or I am getting correct or not. Okay, I am getting this, so please cross check and tell me. Oh, is it 5?
Ma'am, ID is 5
Oh, okay,
milliamp,
okay,
not
sorry.
0.5. Yes, ma'am.
So then what are you getting? Minus 1.24.
Negative 1.24
Okay,
volts.
let me check.
Yes.
Minus 1.24. Okay. Okay. So you have got Vs 2.5 volt. You have got VGS minus 1.24. Now what is VG? VG minus Vs, right? So sorry, what is VG? So what is VGS? It is VG minus Vs. Okay. So what is VGS? It is VG minus Vs. So minus 1.24 VG minus 2.5. So what is VG? 2.5 minus, what is it coming? Is this correct? Now you have found another relation. What? This relation here, right? This one. And in the right hand side, this is the relation, right? Now from here, both of these, 10. Please solve this and tell me the relation between what you are getting. So, okay, one more thing. R1 plus R2 is given as 100 kilo ohms. This was given. Now tell me the value of R2. Is this correct? So all these calculations you have to be very fast. Okay. So most of the time you should be able to do it on hand, because you have in gate you have to use the computer's calculator, which makes you slow, right? So better to do calculations like this. And even when you are doing heavy calculations, try to use the calculator which is there in your laptop. Don't use the scientific calculator, because if you keep on using the laptop's calculator, then it will make sure that in gate also you are in practice, right? Okay, so am I correct here or is it wrong? Please let me know. So this will make your R1 100 minus 62.6, which is 37.4 kilo. Please let me know if it is correct. So Rudra Lakshmi, are you there? So I'll be calling randomly people so that I know that you are following. Okay. So please be attentive. Soumyadeep Kar. So is this correct? Have you been following?
Yes, ma'am.
Okay, okay.
Yes, ma'am. I'm following this.
So now you have found R1 and R2. What is left? So they had asked you to design the circuit. You have found R1, you have found R2, RD is left, right? So RD is again simple because you know ID, and you know VDS, you know VS. So what we will do? Again, let me go to this. Okay. So here we found VS. VS was what? 2.5. We found VS. Okay. And what will be VD? You don't know because RD is not given, right? So VDS is what? VDS is, right? So if I can find this value, I will be able to solve. Or else what I can do, I can simply put a case KVL here. I can either put a KVL here in this loop or in this loop, and I will be able to no, sorry, that won't give me. So I have to put this entire KVL and find the value, right? So VDS is 5 volts. VDS is 5 volts. So 5 equals to VD minus 2.5. This gives you VD as 7.5 volts, right? So VD is 7.5. That means KVL. Okay, so we need not put the entire KVL because VDS is already there. So I'll put the KVL here till VDS, VD value. Okay, so VD here is nothing but like this, 7.5 volts, right? And VS is nothing but like this, 2.5 volts. So that VDS is 5 volts, 7.5 minus 2.5. Okay, so I'll directly put a KVL there. The KVL is minus 5 plus IDRD plus VD equals to 0. So IDRD equals to 5 minus. So how is it coming negative? What did I do wrong? VDS 5 volts is given, right? Or DC drain to source is 5. So VS is 2.5. Then that has to be 7.5. 1 second, let me just check it once in the book, the values, because I'm getting a negative value here. Oh, nobody pointed it out. So here you see minus Vs plus IDRS minus 5 equals to 0. So Vs is basically, it is minus Vs is equals to 5 minus IDRS. So Vs is actually a negative voltage, right? It will be minus 2.5 volts. Which makes sense because the VGS is negative, right? So okay. So Vs is minus 2.5, and then here it will be plus 2.5, so that when it goes through this side it is minus, and this will be minus 3.74 volts. So again this is my mistake. VG is basically we got VGS to be positive, so we could have cross checked and it did not, it skipped my thing that VGS should be negative for an NFET, and VGS was coming positive the way I had solved earlier. So I hope the thing is clear. VS was negative. I missed the negative sign. So VS is minus 2.5 volts. And if you put the value, you will get VGS minus 3.74. And here again, if you put, this will be minus 3.74. Okay. So now you solve and tell me what you are getting. So any one of you should have pointed this out. Anyways, 5 minus 3.74 into 10, 12.6 kilo ohms. Is this clear? Whatever I have done wrong? So this should be the answer. Okay. So now let me see. VDS is, this is also wrong obviously, because VD cannot be 7.5 when the total voltage is less. So VDS is 5 volts. VS is minus 2.5. Okay. So that this will be plus and VD will be 2.5. Okay. So if VD is 2.5, then RD is 5 minus 2.5 by 5, 2.5 by 5.5 kilo ohms. Okay. So finally you had to find three values, R1, R2 and RD, which is 0.5 kilo ohms. Is this clear? Now it is correct. So I think we will solve the third question in the next class. If you want, I can give you that question. You can solve it yourself. So is this clear, or should I explain it to you once again? Just let me know what you want. Clear, right? Okay. So you understood the mistake that I did, right? So Vs will be negative. VGS is always a negative voltage. We were getting positive. So like that, as I had explained earlier, we can always cross check. Okay. So then do you guys want to see the third question? Want to try it yourself? Then we can take it in the next class with, then I'll start with the MOSFET after that. Okay. So this is the question, you guys can note it down and you can follow Donald Niemann's book for more such questions, but not very much practice is needed in JFET. We don't know if it will be a very important topic or not. MOSFET will definitely be more important, but solving these problems will definitely act as a base. Okay, and it might be asked also. So please take a screenshot or note this problem and then we will end the class. Okay, so please reach out to your friends as well who are preparing. Tell them what all is going on in this NPTEL sessions, not only mine session but other sessions as well. If they can be benefited from this, because the main thing is live interaction. Okay, in YouTube videos or in NPTEL videos, you cannot do that live interaction where what you can do here. So I would rather suggest you to please be present on time in this class and please ask others whom you know to please join it, because it increases my enthusiasm level as well. So there are 20 people less today, so that is not a good thing. It would be good if you can please join. It might be because I am actually uploading the YouTube videos, so people would have thought that okay, when we can get to see the YouTube, why join the live class? But the main idea is joining the live class and asking me questions, right? So as and when needed, I'll be telling you the tips of gate, whatever I used to use. If you want me to take some part of this KVL, KCL, voltage division, superposition rules, Thevenin, do let me know. We can have a class on that also if others are not covering it. And if you have any doubt, we can uh, take this. Chandrasekhar has asked, ma'am, like EDC that you had told the hot topics which are asked more in recent years. Can you also tell? Yeah. So in analog, actually, I had told some of the topics in the first class, I think. So next class, or maybe after that, next to next class, I'll prepare a list of topics and give it to you. I wanted to finish up with the MOSFET first, because I think MOSFET is one of those hot topics that are going to come. Now the focus is more towards MOSFET than BJTs. Okay. So MOSFET in recent time has become very hot topic. CMOS inverter is a hot topic, and op amps is an evergreen topic. It will always be there. Op amps will always be there. Okay. So prepare these three things well. Op amp, I can tell you very interesting concepts in op amp. So once we finish with the MOSFET, we will start with op amps. Okay. So keep studying, keep practicing, keep working hard. Let's meet in the next class. Okay. Okay then. Bye.